Hey guys, I'm Jed. Welcome back to my LeetCode review one take vlog on 212th problem, word search second edition. We are given an m times n board of characters and a list of strings words. We need to return all words on the board. Each word must be constructed from letters of sequentially adjacent cells, where adjacent cells are horizontally or vertically neighboring. The same letter cell may not be used more than once in a word. And let's see the example 1 here. We got m times n board here, which is 4 times 4 board. Then we got several words we need to search on this board. And the final output is eat, which is E-A-T here, and oath, O-A-T-H here. So our output is eat and oath. And let's see the example 2 here. We got 2 times 2 board, and we need to find the word A, B, C, D. The output is an empty list because A, B, C, D is not horizontally or vertically connected. Then let's get started with the intuition of this problem. We need to find multiple words from a given list in a 2D character board. Each word must be constructed by traversing adjacent cells. We can only move horizontally or vertically, but not diagonally. And we can reuse cells for the same word. So we can think of 2 approaches to solve this problem. The first approach is brute force. For each word in the list, we search the entire board to check if it exists. This would involve a depth-first search for each word, and the time complexity is W times M times N times 4 to the power of L. W means the length, means how many words we need to search. M is the number of rows, N is the number of columns. And 4 means we have 4 directions, up, down, left, and right. And L means the length of this word. And we can also have the second approach, which is try plus depth-first search. We can build a try, which is also called a prefix tree, from all the words in the list. Then we perform a depth-first search from each cell on the board. This allows us to search for all words simultaneously rather than one by one. And we can terminate early if a prefix doesn't exist in any word. So let's implement the try plus depth-first search approach because it is more efficient. All right. Before we start, we can talk about the brief solution. First, we'll build a try from all the words in the list. Then, for each cell on the board, we start a depth-first search exploration. During the depth-first search, we'll check if the current path forms a prefix that exists in the try. If a complete word is found, we'll add it to the result list. And the final state, we'll use backtracking to explore all possible paths. Then, let's get into our code. First, we need to define our try-node class to store the dictionary of words. Let's call it class try-node. Inside the try-node class, we'll declare an array of children nodes. indexed by character A to Z. Try node array called children. Then we declare another variable called word. If this node represents the end of a word, we'll store the entire word here. Next, we'll implement the constructor to initialize a new try node. Public try node. Inside the method body, we'll initialize the children variable get new try node at 26 size because we have 26 letters. Then we'll initialize the word variable as now. Word gets now. Alright, let's go back to our solution class. And we need to declare several static variables. Private static final integer arrays called directions gets -1 0, which means the direction of up, and 0 +1, which is the right direction. Then is 1 and 0, which is the down direction, and final left direction 0 and -1. Next, let's go back to our find words method. First, we'll initialize a list to store the final result, found words. List of string. Let's call it result. Gets a new array list. Then we'll handle the edge cases where the board or words array is empty. If board equals now, or board dot length equals 0, or board of at index of 0 dot length equals 0, or words equals now. Then we just return the empty result list. Next, we'll build a try, which is the prefix tree from the list of words, so we can have an efficient prefix check. Try node. Oops. Root gets build try. Build try would be a new method we need to implement in the following code. Then we need to get the dimensions of the board, which is the number of rows and columns in the board. Integer n gets board dot length. Integer n gets board at index 0 dot length. N is the number of rows of the board, and n is the number of columns of the board. Then we'll start a depth first search for each cell in the board. So we create a for loop here. I started at 0. When I is less than n, will increment I after each iteration. Then we implement an inner for loop. Integer j started at 0. When j is less than n, we'll continue this for loop. Oops. We'll increment j after each inner for loop. Inside this body, then we'll perform a depth first search method for each cell. Depth first search method with board, the index of row and index of column, and the root node, and final result list. The DFS method will be the new method we need to implement in the following code. Out of the outer for loop, then we just return the result list. Alright, now we need to implement the build try and depth first search method here. And let's implement the build try method first. Private. The return type is try node, and the method name is build try. The inputted parameter is a string list. It's a string array called words. Inside the method body, first we'll create the root node of the try node called root gets new try node. Then we'll insert each word into the try. We'll create an enhanced for loop. String word in the words array. For each word, we'll start from the root for each word. Try node gets root. Then we process each character in the word. Enhance for loop, character C in word to character array. Oops. Inside the for loop, for each character C, we need to calculate the index for the current character. For example, A is equivalent to 0, and B is equivalent to 1, and so on. Integer index gets C minus character A. Then we'll check if the child node for this character exists or not. If it doesn't exist, we'll create it. If node.children of index equals now, then we create a new try node. Gets a new empty try node. Then we'll move to the child node for the next iteration. Node gets node.children of index. After processing all characters, we'll mark this node as the end of the word. Node.word gets the string of the word. Finally, we'll return the root node of this constructed try. Alright, that's all of the code for the method called build try. The final step, we'll implement the DFS method to explore the board and found words. Private void that for search with 5 parameters. The first parameter is a character to the array called board. The second parameter is the index of row, and third parameter is the index of column. The fourth parameter is the try node, that's called node. And the final parameter is result list. At the very beginning, we still have to get the dimensions of the board. M gets board.length. Integer n gets board of 0. Dot length. Then we'll check for boundary conditions, or if the cell is already visited. If the cell is already visited, it will be marked with a special character. Let's call it the sharp character. If I is less than 0, or I is bigger than, or equal to m, or j is less than 0, or j is bigger than, or equal to n, or board of I, j equals the special character, sharp symbol, or hashtag symbol. Then we just terminate that first search method. Otherwise, we'll get the current character from the board. Character C gets board of I, j. Then we'll calculate the index for the current character. Integer index gets C minus character A. If this character doesn't exist in the current try node, we just return to terminate this method if node not chosen. Of index equals null, we just return. Or we'll move to the child node corresponding to the current character. Node gets node dot chosen of index. Then we'll check if we found a complete word at this node. If so, we'll add it to the result. If node dot word is not equal to null, then we'll add a word to the result list, and we'll set the word to null to avoid adding duplicates if we revisit this node. Node.word gets null. After that, we'll mark the current cell as visited by replacing it with a special character, a hashtag character. Board of I, j, gets a special hashtag symbol. Then we'll explore all 4 adjacent cells, up, down, right, and left. We use an enhanced for loop called integer array a variable called direction. Directions. For each direction in the directions array, we will calculate the coordinates of the adjacent cell. Enter new, let's say I, gets I plus direction of 0. Enter new j gets j plus directions of 1. Then we'll continue the depth first search method for the adjacent cell. Depth first search method of board new I, new j, and node, and the final result list. After this for loop, we'll restore the original character, which is the backchecking state. Board of I, j, gets c. Alright, that's all of the code. Let's submit our code and check the correctness. Oops, there's a compile error here. Variable board is spelled wrong. Let's check, let's revise it. Is at 16th line. Okay, let's resubmit again. Yes, our code got accepted. Now, let's analyze the time and space complexity. So, for the time complexity, we'll define several variables. For example, m is the number of rows in the column, in the board, and n is the number of columns in the board. W is the number of words in the input list. And the fourth variable, L, is the maximum length of any word in the list. Talking about the time complexity, and there are several factors. The first factor is the process of building the trie. For each of the W words, we have inserted all characters into the trie, and for each insertion, it takes big O of L time, where L is the word length. So building the trie takes big O of W times L time complexity. And the second parameter, the second factor, is depth first search explorations. As we start a depth first search from each cell on the board, and we have m times n starting points. Then, for each starting point, we need to explore in 4 directions: up, down, left, and right. Next, the maximum depth of recursion is bounded by the maximum word length L. So, the overall time complexity, it is big O of n times 4 to the power of L. Alright, so the total time complexity is W times L plus big O of m times n times 4 to the power of L. Then, let's get into the space complexity. And there are 3 factors. The first factor is called the try storage, because in the worst case, if all the words have unique prefixes, we need to have W times L nodes in the try. W times L in the try. And the second factor is the recursion stack, because the maximum depth of the recursion stack is L. L is the maximum length of any word in input list. Recursion stack. And the final factor is the result list, because in the worst case, we could find all the W words, and we need to store all the words in result list. So the final space complexity is W times L plus L plus, plus W times L. Alright, this is the end of my LeetCode review vlog on this problem, word search, the second edition. And I highly recommend you guys to visit my online GitHub page here, which contains all the problem description, intuition, main idea, and the final detailed solutions with very detailed annotations for each code, and the final time and space complexity analysis. You can see here. And you can also visit my GitHub repository here, which contains all the codes and nodes to build this online GitHub page. And thank you guys for watching. I'll put those two links on my YouTube description below. And see you next time. Bye bye.